Hey everybody, it's Ripley. I know that you are sick and tired of using these definitions of derivatives, right? They are the worst, especially when you know that there has to be something better around the corner, right? There has to be. All right, f of x plus h minus f of x all over h, all right? They are a pain in the butt, especially when we know things like, what if I take, we're going to make rules, that's all we're doing, and we're going to prove rules and talk about rules and all that good stuff. It won't take very long, so bear with me. What is the derivative of a constant? Well, think about that. Visualize what y equals c looks like. It looks like that. That's y equals c. It's a horizontal line. Well, all lines are their own tangents, right? All lines are their own tangent lines. That's what a tangent line does, is it basically distills a function. Excuse me, I'm going to have a sip of Coke here. It distills a function down to a linear thing rather than a curved thing. Well, a line's already linear. What's the slope of a constant? Ta-da! It's 0. Nothing to it. All right? So think about that. This is going to do, we're going to do, I don't know, we'll just keep adding them. So what is, that said, what is the derivative of that guy? Well, again, if we can visualize the function, it makes our lives real simple to start coming up with these rules, right? That any line is its own tangent line, and the slope of that tangent line is simply the slope of the line. Booyakasha. How about any line? If I do take the derivative of mx plus b, well, again, if we think of this as y equals this, it's just a line. It's already got a slope. It's already its own tangent line, so the derivative is nothing to it, okay? Now, this one's going to get a little bit beefier, okay? We're going to write it up, and then we're going to prove it. All right, what is the derivative of x to the n? All right, now no limits or any of that stuff were required for this. This stuff was just intuitively known because they're all lines. But we're going to do a little bit of proof with this one. Not too nasty, but a little bit of one. All right, now hopefully intuitively with all that awful algebraic garbage that you had to do with these two, all right, you started getting an intuition. Your spidey sense started to tingle, as it were. The derivative of x to the n is nx to the n minus 1. That's all that it is. All right, now we're going to prove this. And any time that you have to prove something about a derivative, I'm going to say this no fewer than 14,000 times. Excuse me, before the end of the year. But what we're going to do is we are simply going to take, we know that the derivative of this is if we have f of x equals x to the n, then we're going to look for f primed of x, and our claim is that that is nx to the n minus 1. So let's just start with the limit definition of this guy. I'm just taking this function. I'm going to do the limit definition. All right? So I got x plus h to the n minus x to the n all over h. All right. So this is going to be our proof. Let me write that up. It's sort of a proof. I'll asterisk it because we're not being exhaustive in this proof. Now, I want you to think about something here for just a sec, all right? So we're going to play with Pascal's thing real quick. I want to show you what Pascal's thing, Pascal's triangle. Try that again. So think about this. If I take x plus h and I raise it to the 0, what do I get? I get 1. If I take x plus h plus h as opposed to just x plus h, what a ding dong. If I take x plus h, and I raise it to 1, I get, well, let's look. Now, we're just going to do Pascal's triangle, so I'm going to do the coefficients, right? I'm going to do a 1 here and a 1 here. Remember how Pascal's triangle works? So if I do x plus h and I square it, I get x squared plus 2xh plus h squared, right? But the coefficients are just 1, 2, and 1, right? If I do x plus h to the third, I get, now remember how Pascal's works? You've all seen me do this, God bless it, so I'm hoping I don't have to explain it too much. 3, 3, 1. right? Let's do one more, just so we can look at this. X plus h to the fourth. Remember how this works? 1, 4, 6, 4, 1. Now, let's go down a little bit. Let's go all the way down to x plus h to the n. And let's think about what really happens here. I'm going to have a 1 here, right? My next term is going to be a what? What do you notice happens here? Remember how these play out. Like if I were to actually write this up, this is just a 1. This is an x plus h. This is an x squared plus 2xh plus h squared, right? This is an x cubed plus, now wait, how's this one work again? It's 3x squared h plus 3xh squared plus h cubed. Remember that? Now what are you noticing? Look at these second terms. What do you notice? Look close. Okay, that's a 2. I used to have an x squared, and now I have a 2 in front, and this is now a 1. I used to have an x cubed. This is now a 3 in front, and now I have a 2. And all these other terms have h's in them, don't they? Every last one of these terms is going to have an h. So after the first one, I'm going to have a whole bunch of terms with h's in them. So I'm going to cheat a little bit. I'm just going to say 1 and then plus. Now remember, this 1 really represents x to the n. Remember? Because this first term is going to be x to the fourth plus 4x cubed h plus a whole bunch of terms. We'll call these h terms because they've all got h's in them. Now that becomes really important. I'm going to have an x to the n, and then I'm going to have my next term, notice again, x to the fourth, 4x cubed. So plus nx to the n minus 1 times h, and then a whole bunch of h terms, plus a bunch of h terms. Now, why did I do that? Well, let's look real close. Let's stumble this away. I'm going to do this, and watch what happens. This is really fun. This term right here, let's rewrite this term right here like this. So this becomes the limit as h goes to 0 of x to the n plus nx to the n minus 1 h plus, I'm going to call these h terms. All right? Now, one thing I do want you to notice is that all of these h terms really have a degree that's higher than 1. It's bigger than 1 because of the way that a binomial expansion works. So this is what this is right here. And then I subtract out my x to the n, and I divide by h. Watch what happens. Goodbye, goodbye. Now look close. This becomes the limit as h goes to 0, those look like n's, don't they? As h goes to 0 of nx to the n minus 1 times h plus, now since those guys all canceled, I'm going to call this my h terms. And these h terms have a degree higher than 1. Now why is that important? Watch. Because this h cancels with this h, and then it cancels with a whole bunch of these guys. But I have additional h terms in there. Now, why is that important? Because as h goes to 0, sorry guys, I'm going to change the color to be more dramatic. This whole term goes to 0. That h and that h canceled, and all of these h terms, because they had a degree higher than 1, so they're still floating around in the abyss over here, right, in the ether of this problem, and the only thing that I'm left with is nx to the n minus 1. I love that proof. Such a cool proof. Okay? So that's a biggie. That's a biggie. That's going to do the lion's share of all of the derivatives that you're going to take in this class. That's like home base.